I'm glad that I can provide James with a short break uh, by presenting to you SYCL bindless images, an extension to DPC++ that my team and myself at CodePlay have been working on. So in this presentation, I'm going to give you a quick introduction, talk about the importance of images, why they matter, and then also a brief history on bindless textures. I'll move on to talking about why current SYCL images are really not sufficient at all. And then I'll move on to talking about the meat of this presentation, which is our extension, bindless images. We've also got a little bit of a additional interop functionality, which I'm happy to talk about. And then, yeah, the Q&A at the end. So the first thing I want to emphasize is that the use case of images extends way beyond just what is physically rendered to the screen. Take, for instance, a depth map, which is an image that relates to the distance to an object from a viewpoint. So what makes an image, a use case for an image over just a simple buffer is the hardware units that provide certain functionalities like filtering and addressing modes. And this is what is usually considered as sampling the image. So with filtering, what happens is that you can essentially take your discrete pixels and be able to convert it into a continuous map that you can index in between pixels, and the hardware will linearly interpolate between those pixels. Any kernel may benefit, which requires this kind of functionality, would benefit from the hardware units that are dedicated toward these tasks. So despite our extension being very experimental, we already have quite a few interested parties and some who are either actively already making use of SYCL bindless images, take for instance Blender, I'll speak more about them near the end, or are also waiting on our extension. So our story begins a little under 15 years ago with OpenGL. So OpenGL had evolved to replace the manipulation of the state variables of the context directly with the binding of objects to that context or to other container objects. And since the API stream was greatly reduced, this gave a massive speed up. However, this explosion in objects bound to the context or bound to other objects essentially led to pointer chasing and just in general L2 cache pollution. Every time a bind operation was done, the driver would have to fetch object data from system memory so that it could do what it needed to do. So each bind, you could be getting several reads of object data, and each read could involve multiple dereferences. And when you combine that with the LRU eviction unfriendly nature of graphics applications, yeah, you were basically just running into a non-stop barrage of cache misses. And then NVIDIA aptly named this the modern CPU bottleneck. So what do you want to do? You still want to use objects, but instead more directly, just by the GPU address, or more preferably, a handle. With just this minor change, NVIDIA reported a 7x speed up in one of their showcase examples. This change was then introduced to OpenGL as an extension around about 2009, and then eventually was added to CUDA around 2012 as bindless textures. So now transporting back to the present day, all modern GPU APIs work this way. And since SYCL images makes use of these APIs as backends, then surely there's no performance boost to be expected then. So what exactly is the problem? If you just Google bindless images, it'll only lead you to the preceding history lesson I just gave you. And I certainly know I tried to Google it. So now imagine yourself as a programmer working with SYCL images. You're going to find yourself running into a lot of rigid abstractions that make SYCL images very difficult to work with. You're going to find a lack of flexibility, weak developer control, a lack of features. And if you're trying to port your CUDA code using a porting tool like Cyclomatic, then you're going to be having a very difficult time. So what do I mean by these four points? So rigid compile time constraints make it very difficult to work with SYCL images in a dynamic and flexible way. Take, for instance, the number of images must be known at compile time, meaning no dynamic arrays of images, and special image types like virtual texturing are impossible. Virtual texturing is where each data point of an image contains a reference to another image. Even with static arrays, there are constraints on how you store your image in those arrays. Take, for instance, each image must all have the same number of dimensions. With SYCL images, we have no choice over how the images are stored on the device. Is it in a device-optimized layout, linear, pitched? Got no choice. We can't even have images backed by USM. There's no distinction between device image data and the image itself, and there's limited choice over how the image data is copied to or from the device. And when it comes to features, SYCL images are very lacking. There's a shortage of image types, a shortage of sampling capabilities, and image data copying capabilities. And this one speaks for itself. Due to the rigid abstractions of SYCL images, there's a poor mapping to modern GPU APIs like CUDA, making porting your non-SYCL code very difficult. And now, SYCL Bindless images to the rescue. So I want to emphasize that this extension is very experimental still. Everything I'm about to show you could change quite a bit. I think I've even got a couple things coming up that I can point out is already changing. So SYCL bindless images are inspired by the lightweight nature of CUDA bindless textures. What results is an API that is very flexible, fully controllable, feature-rich, and conforms very well to modern GPU APIs, which will make translation much easier. The two pillars that define our extension to enable this are that we separate data allocation from image creation, and that we treat all images as simple opaque handles. So what does this look like? If you're trying to store your image memory in a device-optimized format, it'll be handled through a very simple opaque handle, which we have called image mem handle. We also provide our AII wrapper, image mem, for this handle, which does all the allocating and destruction for you. And it contains all the useful information about the image, like the descriptor. And then the descriptor, this is basically what represents all the possible supported image properties. So your things like the width, height, channel order, and type, and even the properties to define bitmaps and image arrays. Do take note that we're bringing back SYCL 1.2.1 image channel and type. And what I can say is actually, this is one of those things that is changing quite recently, I think. We'll be changing channel order to get rid of that and just say channel size as we bring in the channel reordering feature. We also make sure to perform, because our extension is experimental, we make sure to perform error checking in the constructor so that no invalid descriptor can be constructed. And so how would you actually allocate image memory then? It's very simple. With the RAI wrapper, you just populate the descriptor with the appropriate values, and you can construct your image mem. But of course, there are the standalone functions to do the exact same thing. But we also provide a new USM allocation that pads image rows so that it is optimized for device memory access, obviously dependent on your access pattern, pitched alloc device. So this is used to prevent situations where two threads are attempting to access the same or overlapping data from local memory, known as a bank conflict. This allocation is for 2D images only, and the USM is on device only. And then, of course, with our new allocations, we have to provide the additional copy functions, which you can see here. And what we currently support is host to device and device to host, but device to device is being worked on, so hopefully that will be coming in very soon. And one of our highlightable new features is sub-region copies. So we can copy over data to just subsections of an image. And then the image handles. So we treat all images as simple opaque handles, and we provide two different handle types that represent basically all the currently implemented image types. So these are sampled and unsampled images. Obviously, by their name, an unsampled image is one where no sampling is performed, but a sampled image is where we can access the power of sampling, like filtering and addressing modes. And yeah, these handles are very simple to create and then use. So because of their simplicity, they're easily passed to the kernel. And when it comes to the distinction, why we have an unsampled versus a sampled, well, this provides useful compile time constraints, such as preventing the application doing things that it shouldn't, like writing to a sampled image. And it maps very well to other APIs like CUDA, HIP, and even SYCL 2020 with their sampled and unsampled images. So an unsampled image, it can support reading and writing, but it can only, as of right now, it can only be backed by device optimized layout allocation. So that means no USM for an unsampled image. But with a sampled image, it's more interesting since you get the access to the hardware sampling capabilities, and it can be backed by both a device optimized layout or USM. So note here the sampler, which I'll talk about in a minute, is tied to the handle on the creation of the image. This is another thing that's may change in the future, but we'll see. And then creating the handles is very simple. Just pass in your memory handle and the descriptor to the create image function, and that's it. But obviously with the sampled image, you must also pass in the sampler. And now the sampler, we've created a new sampler object. And we wanted to do this so that we could add a whole new set of capabilities. You'll see I've put the list of the sampling capabilities that we have. An equals means that it was already previously there in the original SYCL sampler object, while a plus is the new things we've been adding. And finally, actually using them. So using them in the kernel is very simple. Both unsampled reading and sampled reading is facilitated with sample image and fetch image, while writing is done through write image. So the thing to note here is that unsampled images are indexed with integer coordinates, while sampled images can be indexed with both floating point coordinates and integer coordinates. So the fetch image, essentially that represents fetching the data from the image without applying any sampling capabilities. So you can do this with a sampled image. It will simply ignore the sampler and just return the data unfiltered. Whereas sample image obviously does sampling. But we also allow for the reading of images with user-defined types as well. You must pass in a hint type so that the API can perform the correct sampling operation, because the way the image is sampled does depend on the underlying data. And we've also been adding new image types, and I can say that with cube maps, this got merged in, I think, on Tuesday. So got it in on time for this. So we've got MIP maps, image arrays, and cube maps. So the main point here about all these different image types is that the code required to make use of them is very similar between them. You just have to make sure that the descriptor is constructed appropriately, and then yeah, it just works. There is some nuance required with MIP maps, however, because you must copy to them on a level by level basis only. So in this example, actually, you can see an image array is being allocated, copied to, and created. And on the right, you see the arrow that points that the same code applies to all the different image types. So both the standard images, arrays, and cube maps. So when it comes to these different image types in the kernel, some features are supported while others we won't support. Take, for instance, bitmaps are not going to be supported as an unsampled image. So you would not be able to create an unsampled image handle with a bitmap. And the fetching, which means that you're not applying any sampling to a bitmap, would not be supported. So the way you use these in the kernel is with the, let's say if it's a bitmap, it will be a sample bitmap function. An image array, it will be a sample image array function. And one more thing. We've also been working on additional interoperability functionality to work with SYCL binary images. So this includes the ability to both import external image memory and external synchronization primitives. We've had support for Vulkan for quite some time, but most recently we've been working on DirectX 12 interop too. And then importing external image memory is as simple as just 2 steps. First, you must import the external memory and then map that imported memory to a usable memory object, e.g. An image mem handle or a USM pointer, which is currently not supported, but we hope to provide that soon. At that point, the user is then free to create an image on the imported memory and use just as described throughout this presentation. Currently, we only support the importing of standard and mapped images, but we hope to very soon have the importing of also image arrays and cube maps too. So here's an example of how this is done. You must declare an external mem descriptor with the external handle and the information. Then you create an interop mem handle by importing. And with this interop handle, you can then map it to a usable memory object like image mem handle or a USM pointer. And with that, you can freely use it as however you see fit, create an image on top of it. And importing external synchronization primitives is even simpler with just one stage. Just simply import the external semaphore and you can immediately begin waiting on or signaling them. When importing image memory uses an external mem descriptor and creates an interop mem handle, importing semaphores makes use of an external semaphore descriptor and creates an interop semaphore handle. After importing the external semaphore, you can then use them straight away to directly wait on or signal the semaphore. So, have we managed to achieve our goals? Personally, I believe we have. I think SYCL binary images have addressed many of the problems that plague SYCL images. Our extension is very flexible, it's feature-rich, controllable, and conforms very well to other compute APIs and languages like CUDA. And when it comes to what we currently support and where we plan to take support, we've spent the majority of our time bringing SYCL binary images up on the CUDA backend to work on NVIDIA devices. However, we've also been putting in good work to provide support for Intel devices by proposing an extension to the Intel backend level 0 and an extension to SPIR-V that Intel devices can work with. As I speak, SYCL binary images is being implemented on the level 0 backend, and some of our tests are beginning to pass. A first revision will likely implement standard SYCL binary images functionality, including basic interop too. And in the future, more advanced features like additional image types will be added. AMD and HIP are a lower priority, but we know that it would be a straightforward port from the CUDA implementation, so hopefully we can get to that this year. And unfortunately, there's no priority at all for OpenCL. We likely won't be thinking about OpenCL for quite some time. So we're currently working towards our 6th revision. The extension is now available. It's available now on DPC++ and is constantly being updated with new improvements and fixes and everything. And then as for the future, we're going to continue adding support for binary images in Intel devices with a level 0 implementation and SPIR-V extension. AMD and HIP is in our peripheral, so hopefully we'll get to that this year. but the focus is on Intel devices. We're also going to be working very closely with Blender to begin profiling, benchmarking, and optimizing our extension. We haven't had a chance yet to look at performance, and entering this phase of the project is going to be quite exciting. And then as for future revisions of the project, we're thinking about many quality of life improvements, as well as big ticket items like combined image types. So that would be something like a MIP-mapped cube map. And then also additional interop functionality, so more APIs, more image types, more resource types, and maybe the ability to export image memory as well. We're also interested in preparing a Khronos extension to replace SYCL 2020 images with Bindless images. And we also know that we've had some interest in integrating Bindless images in SYCL Next. So yeah, that's me. Thank you.
Hi, Sean. Good talk. What kind of technology are you using to implement this, like Vulkan or something?
Sorry?
Are you using Vulkan to implement this?
No. So this is done on the CUDA backend.
Okay. Yeah. And for level 0?
And what?
For level 0?
For level 0, it's on the level 0 backend.
Okay. But I guess that they will be using something like that, right?
What do you mean?
Like underneath level 0 will be using Vulkan or something to implement this, or what are they using? Do you know? Did you work on this?
I'm not sure how the level 0 team is going to be implementing it, but